This next one is also a named type of series. It's called the harmonic series, and it is a divergent series. So we'd like to show that it's a divergent series. We don't have any formulas for it, so let's take a look at some partial sums. The way that this one works out is it is convenient to look at powers of 2 partial sums. So the second partial sum would be the first one and the second one together, 1 plus 1/2. The next power of 2 partial sum would be 2 to the second, or 2 to the fourth partial sum. So that's the first 4 terms. So 1, 1/2, 1/3, 1/4. And the idea here is that you've got a 1, you've got a 1/2, and then you've got this thing right here, which is larger than a half. So we can say that this is larger than 1 plus 1/2 plus another 1/2. That is a quarter plus a quarter, right? It's larger than that. So what you're looking at is S sub 4, the fourth partial sum, is larger than 1 plus 2/2. And why didn't I just write 1 plus 1 or 2 here? You'll see why in a second, because we're trying to establish a pattern to do this. The next one would be the 8th partial sum, so we want the first 8 terms. That's 8. Okay, so again, we have the same idea. You've got this 1, you've got that 1/2. That is going to be larger than a half. 7, oh, one more. And then that is going to be 1/5 is a little bit larger than an eighth. 1/6 is larger than an eighth. 1/7 is larger than an eighth. 1/8 is 1/8. So what we're going to say is this thing is larger than 1 plus a half plus a half plus a half, or 1 plus 3/2. So we're trying to find this pattern. Do you see the pattern yet? The second partial sum is 1 plus 1/2. The fourth partial sum is larger than 1 plus 2/2. The 8th partial sum is larger than 1 plus 3/2. So what's your guess for the 16th partial sum? Greater than 1 plus 4/2, right? So what would the S2 to the nth partial sum look like? 1 plus, well, it would be greater than 1 plus n/2. So if we have this nth partial sum, and we take the limit as n approaches infinity, this is infinite, and since the nth partial sum is divergent, that means the sum of this series is also divergent. We cannot add these up to find a finite number. Okay, we've got a couple theorems which will allow us to test to see whether or not we should even bother to see if a series is convergent or divergent. So, first theorem, if the series is convergent, then the limit of a sub n equals 0. So what we're saying is, in order for if the series is convergent, then this a sub n has to be getting small, small, small. So at the end, we are adding very small amounts here. And our test for divergence is if the a sub n does not exist, or if the a sub n is not approaching 0, then the series is divergent. So this is a very simple problem. If we look at this limit of the a sub n squared over 5n squared plus 4, you could probably just look at that and find the limit. Multiplying the top and the bottom by 1 over n squared gives us 1/5. Then by the test for divergence, we know that this diverges. Next, we combine series together with addition and subtraction, and also we can factor out constant terms here, and then we will use those, put them together to find the sum of the series. So we're looking for this sum of the series. I'm going to use those properties, and I'm going to rewrite this to make it look more like something we've done in the past. If we want, we could use the test for divergence. Now, one thing to note about the test for divergence is that just because the limit goes to 0 does not imply that the sum is convergent. We just saw in the harmonic series the limit of the a sub n term, that is the limit of this part, goes to 0, but the series was divergent. So we can't say the converse. The converse is if the limit goes to 0, then it is convergent. We cannot say that. We can say the contrapositive, that is, if the limit does not go to 0, then the sum is not convergent. And that's actually this. This is the contrapositive. Okay, so back to our problem. Right. I'm going to rewrite this as 3 times the sum of 1 over n times n plus 1 plus the sum of 1 over 2 to the n. N goes from 1 to infinity, n goes from 1 to infinity. Okay, so in this problem, we see 3 times 1 over n times n plus 1, and we know that that is a convergent series because it was the telescoping series we saw earlier, just a little while ago, and we know this is going to be 3 times 1 from before. For the next one, it looks like a geometric series, except we would like to rewrite this part as the sum of 1/2 times 1/2 to the n minus 1. Now it looks like our sum of a geometric series, so plus a over 1 minus r gives us 3 plus, that's a 1/2 over 1/2 is 1. So it looks like 4. And that's it for that problem.